So good morning and welcome everyone to this lecture. This lecture is actually offered and co-sponsored by the EDS, so Electron Devices Society chapter in New South Wales, as well as the Electronic Material Technical Committee of the Electronic Devices Society, represented by Mohammed Hossein here, also on the call. So good morning, everyone. And while we have a few other people joining in, so it's morning here in Sydney and different times at different places in the world. Here in Sydney, I would like to make our usual introduction, which is also an acknowledgement to the country. So we are here in the lands of the Gadigal people, who are one of the major people of the Eora Nation, and I would like to acknowledge them as traditional custodians of this land and pay my respects to the elders, both past and present. And as I said, this lecture is sponsored by IEEE Society, Electron Devices Society specifically. So technology for the advancement of humanity. And I think that today's lecture by Professor Kalantar-Zadeh is a very good example of that. So before I leave him the floor, I will just introduce him very briefly. So Professor Kalantar-Zadeh is at the Chemical Engineering Department of the University of New South Wales here in Sydney. He's also a laureate fellow, class 2018, of our Australian Research Council. And he has quite a string of accomplishments that are outstanding, wrote more than 400 scientific papers, books, part of many highly reputable editorials like ACS Nano, ACS Applied Nanomaterials. Last but not least, he is also a recipient, 2017 recipient of the IEEE Sensor Council Achievement. As well, lately in 2020, he received the Robert Boyle Prize for Analytical Science from the Royal Society of Chemistry. And last note on Kourosh, he's also appeared in the Clarivate Analytics as most highly cited every year since 2018. So again, a very accomplished speaker we have today. And without any further ado, I would like to leave the floor to Kourosh to introduce his talk.
All right, thank you very much for this nice introduction. How about I share the presentation now?
Sure, go ahead.
All right. Okay. Do we have the presentation now?
Yes, you do. Can you just stop 1 second
Sure.
sharing? Can you do one thing? Sorry.
Sure. I have to go back here.
I just need to.
All
Okay.
right.
I have a couple of other people joining in just now. Okay, just go ahead.
I'm trying. Oh,
Yep.
oh, okay. I eventually couldn't do that, but it doesn't matter. Okay. Good. Thank you very much for a nice introduction again. So today, again, thanks. I would like to thank for organizing this. It's always a pleasure to be able to present this kind of works to people across different areas and regions. So today I'm going to talk about liquid metals for creating two-dimensional electronic materials. So you don't see the corner of my sharing that I have the images of people, or you do see that?
We don't see the images, I don't think.
You only see the PowerPoint at the moment.
Only the PowerPoint, correct.
Fantastic, good. So I leave it like this now. All right, so basically it's a work on liquid metals that started several years ago in my group. about 2013, there was a guy from Germany, a student exchange, came to my lab and started working with gallium because he was from a company that used to make Gallium. Gallium is an alloy of gallium. So he brought it to my lab, and I was amazed that it was very similar to mercury, but with some specific differences. I'll talk about them later. I became really fascinated since 2013, 2012. When he brought this, I started looking, playing with this material, and became something that turns from a hobby into one of the main businesses of my lab. So let's go to liquid metals. What are they? We are talking about mercury, for instance, francium, cesium, gallium, and rubidium. They are elements that normally at near room temperature, they are metal. They are liquid. So these kind of liquids, they are flexible, they're fluid. You can mix them together. They make alloys. They have high thermal and electrical conductivity, and they are full of free ions and full of free electrons. Very attractive characteristics. But the reality is francium is radioactive, cesium and rubidium are explosive. So what remains to work with are only gallium and mercury. And mercury is unfortunately out. Although I'm against this kind of conversation that mercury is highly toxic, to my opinion, is not that dangerous, and we can play with it. I remember when I was a kid, like 10-year-old, I had always a full jar of liquid mercury in my toy room, and I used to play with them, and I think I didn't catch any cancer or problems so far, but so far we'll see what will happen to me in the next few decades. But considering the hazards of mercury, what remains of this family is gallium. If we consider gallium and we want to establish a kind of field based on this one element, it's very limiting. So I cheated and say, okay, post-transition metals, anything that has a melting point of less than 330 degrees, I put in the family. I define a liquid metal field family. And it seems that it was a good decision. You'll see in the next few slides how we can move from one element to another and use them. Now let's go back to the representative of this family, which is gallium. Basically, melting point of gallium is 29.8. If you put it on the palm of your hand, it melts. And it's relatively non-toxic. It's not like mercury, it doesn't produce the vapor. It can alloy different metals, different elements, and relatively high concentration, like indium goes up to 25, 30%, tin, 5-6%, bismuth, the same for zinc as well. Make these fascinating alloys. For instance, Again, which is very famous, has 75% gallium and 25% indium. Very interestingly, because after mixing, you increase the entropy of the alloy, the melting point temperature decreases, that of 30 degrees to only 15.7. That means at normal room temperature, it's liquid, very similar to mercury. Now, there is a difference between these alloys or gallium itself and mercury. Basically, if you have gallium, you melt it at ambient condition when you have 21% oxygen around you. It produces a two-dimensional oxide layer on the surface. It's oxide of gallium. Very similar to graphene. We know some of these interesting properties about graphene that makes these covalent bonds across the plane. Here, the bonds across the planes are strong. As a result, for instance, if you print gallium droplets on the top of each other, of course, very small droplets, this two-dimensional material help in holding these droplets together into shapes which are non-Newtonian shapes. So very interesting properties, and we are going to use these properties that I will show you in the next few slides. Can we see this two-dimensional material? Yes, we can. You just take one of the droplets, start shaking it. If you look at it under a scanning electron microscope, you see the wrinkles. These wrinkles are these two-dimensional materials of gallium oxide on the surface. wrinkle it more, they break down, they come off the surface and restack themselves on top of each other and make very disorganized layered particles. Now, today I'm going to speak about some of the properties of these liquid metals. I'm going to talk about nanoparticles made of liquids. I'm going to talk about crystallization that you can see in the processes from liquid metals, heterostructuring, especially 2D materials that we obtain from liquid metals, and phase separation after cooling liquid metals, and how in nano dimensions we can control them. So all of them are fascinating. Of course, there are many more, but I limit myself to these 4 topics. So let's talk about nanoparticles, microparticles, which are made of liquid metals. Here, very similar to when you mix oil and vinegar in a restaurant and you dip your bread into. To have a better mix, you just take your fork and mix them together. You actually apply mechanical agitation. And gradually, oil breaks down, makes a small droplets of oil. But the moment that you stop mixing them, these oil droplets merge together and make the large size oil again. But here, the 2-dimensional oxide, which is formed on the surface, when you sonicate gallium or E-gain, alloy of gallium, under a force, mechanical force, this 2-dimensional oxide goes around it and basically make them stable. So they don't merge together anymore. If you continue sonication, the size of these droplets becomes smaller, smaller, smaller. So like any other nano-sized material, you can start making funny, fascinating things from it. For instance, you can make films of very high surface to volume ratio. These films can be used for many different applications. I just presented one of them here for sensing. We used to, before 80s, it was a very common commercial product. Sensors based on voltammetry of liquid mercury electrodes to sense heavy metal ions. Of course, now we are not allowed to use those kind of electrodes anymore because of mercury. But if you use gallium in liquid form, nanoparticles, the sensitivity that you obtain for sensing heavy metal ions like cadmium and lead will be much, much more. Basically, you can easily go to the sensing limits much less than hazardous limits for human body. Here we published in 2014 or 15. Now it's commercially available and it's deployed across the world. Talking about heterostructuring. So I used to work and still work on 2-dimensional materials. One of the fascinating 2-dimensional materials are transition metal dichalcogenides like molybdenum disulfide. Everybody is claiming that we can make this material on wafer scale, on, for instance, silicon dioxide substrate, and make transistors from this 2-dimensional based transistor. But the reality is, if you do chemical vapor deposition of this material, again becomes a classical nucleation deposition. That means you must have nucleation points, and these 2-dimensional materials grew out of those nucleation points. The center is not 2-dimensional material. And also, for instance, molybdenum disulfide or tungsten disulfide and many other these dichalcogenides, when they grow into triangular forms. And because nucleation happens at different locations on the substrate, they eventually reach each other, grow on the top of each other, or become stitched. They make these very bad boundaries that cause a scattering of electrons and holes. As an electronic material, this is absolutely non-ideal. We can use methods like ALD, molecular beam epitaxy as well, which is very expensive, of course, MB. They are very expensive, they're limiting everything. How about we look at what nature with liquid metal gives us? Basically, gallium, indium, bismuth, tin, we can melt them. In ambient environment, 21% oxygen, they use this 2-dimensional material of 1 or 2 layers of oxide of these metals on the surface. And it's self-limiting because of this Mott-Cabrera oxidation. It happens at the same time, all the oxidation. So it's a single crystal not for all of them, for many of them, form on the surface. You bring a substrate near the surface. Another advantage is the core on which these two-dimensional materials are formed is a metal, is non-polarized. As a result, when you bring a polarized substrate like a silicon or silicon dioxide near the surface, this two-dimensional film of oxide which is formed sticks to the substrate. So very easily you can exfoliate it, put it there. And here is an example. Of course, this is not for gallium oxide, it's for tin oxide. Tin oxide is not self-limiting like gallium oxide, but if you reduce the oxygen in the environment, it becomes self-limiting. When 21% ambient oxygen, this oxide on the surface becomes thicker and thicker, like 5 minutes, 15 minutes, and 30 minutes, and it makes this beautiful color that you can see here. You can take a piece of metal, piece of glass rod, and remove that two-dimensional material. As you see, it sticks to that piece of rod very easily. And very quickly, this yellow layer is formed on the surface and make the two-dimensional material. Yeah, you can repeat it very easily. It's highly, if you do it at exactly the same time, it's highly repeatable, highly controllable. Here, for instance, in this example, you see tin oxide, tin monoxide are formed, and we exfoliated and harvested in the substrate very quickly and very repeatably. And we make different structures and finally make devices like transistors from them. Yeah, we can pattern it. Here, right, like very simple patterning that we apply to silicon. We put the photoresist on the surface. We use a mask, photoresist mask. We expose the photoresist through the mask to UV light. Then we develop it. We obtain the areas which are covered with the photoresist and areas which are not covered. The area which are not covered, we fluorinated it, make this hydrophobic. We remove the photoresist. So we have a pattern of fluorinated material, and then we put a droplet of gallium with an oxide layer on the surface. Then we took a squeegee, remove the metal from the surface. What remains is the metal oxide. So it's a gallium oxide pattern on the surface. You see the pattern here. We can use this gallium oxide because gallium oxide can be used for making wide bandgap transistors, or we can transform it into a sulfide, gallium sulfide, which is also very attractive semiconductors that we have shown it here in this example. We expose it to HCl that produces gallium chloride. And then at very low temperature, we expose it to sulfur at 300 degrees as gallium chloride, transforming gallium sulfide. Here, as you see, very interestingly, because the unit cell of gallium sulfide is made of two layers which are flipped against each other. We obtain two layered gallium sulfide, and as you see from fluorescence image, it's very, very homogeneous on the surface. We make transistors. I'm not presenting the other results in here. So as you see, even with hand, by using, without any special equipment, we could make this. How about other materials? Are we just limited to oxides? No, look at this one. We have the oxide of gallium on the surface. We transform it before to gallium sulfide. How about we expose it, for instance, to something like hydrogen phosphate? We did it at 350 degrees with the hope that we obtain gallium phosphide, which is a very interesting material. But instead, we obtained gallium phosphate. We thought it was a failure, but we look at the literature, we realize the wide bandgap commercially used material as a piezoelectric that can tolerate very high temperature. And we were very happy to see that the piezoelectric coupling coefficient that we obtained from this one layer was almost double that of the bulk gallium phosphate. So basically, it's a very low temperature process. You can obtain very good piezoelectric material, and it is silicon compatible. And it can be used, of course, in many devices that you can imagine, which is as an accelerator, which is used in mobile phones, or in a car accident that releases the airbags. Now, Can we make other materials as another example? For instance, gallium nitride. Gallium nitride, if you know, is a very, very important material in making light, low energy light devices these days. So what we did, we took the gallium oxide. This time we exposed it at 800 degrees to a precursor of nitrogen. We've obtained gallium nitride. We characterized it. The mobility was very good, 20 centimeter square per volt seconds, and made devices basically light. I have, again, I didn't present it here. It's a wide bandgap material. You can make blue light LEDs from it, very efficient. This is a very good example of something else that we did. This is not about gallium anymore. It's an example that you can do very interesting thing with tin and bismuth. Basically, when you mix tin and bismuth at different ratios and you mix them together, you can melt it at above 200 degrees. Here, instead of touch printing, we use a squeeze printing. Basically, we put a droplet between two substrate, we squeeze it, liquid metal goes out of it. What remains is one layer of ITO, indium tin oxide, on each side. Now, ITO glass is very important. It's transparent and it's conductive. We characterize it. We saw that it's made of different domains which are stitched together very interestingly, and we could repeat this many times. That means we could make 2 or 3 layers of ITO on top of each other. Now, the band gap is very wide, so it's super transparent. It's actually much more transparent than ITOs which are used in your mobile phone. What does it mean? Suddenly, the light that's used and generated by the LEDs in the mobile phone in your display needs much less energy for you to see them. So what does it mean that the battery, which 90% goes to the display, can last maybe 10 times more? The transparency of everything become much, much better. But more than that, this is a 2-dimensional material, like a book made of many 2-dimensional pieces of papers on the top of each other. We can bend it without breaking it. As you see, there is an example here. We can bend it, bend it, bend it. The conductivity is actually comparable with the conductivity of commercial ITO glasses which are used in your mobile phones. So it's a really new era in displays, that in making displays, that this kind of process can introduce. It's a new class of crystals of ITO, and it can make a big difference in the near future. Some of the big companies actually are now chasing this to make it very commercial at a larger scale, like Samsung. Now, are we just limited to post-transition metals? It's fantastic that we have these post-transition metals with low temperature, but it's a bit limiting because then we lose the access to a large number of transition metals and the rest. And also, we saw that, for instance, gallium phosphide is not a layered material, but we could deposit a 2-dimensional layer of this material. So can we continue this and find different tricks to obtain new crystals of transition metal compounds? Anyway, expanding it into non-transition metal compounds, my postdoc at the time had an observation. He said to me that it's very strange that when we have E-gain that has gallium indium, or we have gallium that has gallium indium and tin, only gallium is on the surface. So I got my PhD student and I asked him, hey, go and try some different metals and see whether there is a competition between these metals to come to the surface. He went away, and after a few months came back, and this poor guy tried like 50, 60 different metals and established some tables for us. For instance, here is a very brief example of this table and graph that metals like metal oxides like gadolinium oxide, aluminum oxide, hafnium oxide come to the surface against gallium oxide. While indium oxide, tin oxide, copper oxide, silver oxide, they don't go. There is a competition. Eventually, we realized that we can come and introduce a kind of theory that what comes to the surface, Gibbs free energy of that oxide should be less than Gibbs free energy of gallium oxide. So like this, we were able to produce hafnium oxide very, very thin. We are talking about 0.6, 0.5 nanometers of thickness. This is the thinnest hafnium oxide, and if you know, hafnium oxide is used as a gate dielectric in all field effect transistors, which are in all electronics. Imagine at the moment, they are all 3 nanometers. And if you go down to 0.6 nanometers, the turn on off voltage, which is used for them, is only 1/6, 1/5 of the normal voltage we need. So it changes the electronic industry again. Or aluminum oxide is a fantastic material for different applications. I'll show you an example here. For instance, you add aluminum oxide in the bulk of liquid metal, as you see here. You just put some water on the surface. Aluminum wins the competition, come to the surface, and very quickly it basically interacts with the water around this. It produces aluminum oxyhydroxide or bohemite. You can anneal it and produce aluminum oxide. These flakes, because hydrogen produced around them, these hydrogens, they push them to make some gaps in between them. It makes a hydrogel full of this two-dimensional material. What you can do, you can just take a piece of it and use it as a filter. It's the best two-dimensional filter in the world. Why? Because aluminum oxide is known to remove every single escaping ions, for instance, heavy metal ions in the environment. They absorb it into itself to produce the aluminate type of that compound. And also because the gap between these flakes is very small, if just a few nanometers, hydrophobic materials like oil, they can not pass through them and get trapped. So we made these filters of water, and we could use them hundreds of times to obtain clean water from muddy materials. Yeah. Here it is. We only talked about oxide and second transformation to a different compound. Are we able to produce the material of interest directly in one step? Here is tin sulfide. Tin sulfide was a fascinating material. Since 2015, I saw a paper that was published, predicted that the piezoelectric coupling coefficient of tin sulfide is a gigantic 144 picometer per volt. Why it's produced, if you see in the figure, it's a kind of a puckered structure. It's like an accordion, and you can pull it. It can be pulled. As a result, it goes to a non-symmetric structure further and further and produces this extraordinary coupling, piezoelectric coupling coefficient. Now, has anyone made it? No, for the past 5 years, I was amazed to see that no one has been able to make it. But there is a reason for it. There is a natural reason, because the lone electron pair electron of the S in the layers, it's a layered SNS, it's a layered material. The interaction between different layers that comes from this is very strong. It's much stronger than the van der Waals force affinity between the layers. As a result, with mechanical exfoliation, nobody could make it. So what we did, we said, okay, what if we change the oxygen in the environment with a sulfur precursor, which is H2S, and it's very reactive. Actually, we didn't use high concentration of H2S, very poisonous. We used only 50 parts per million in the environment, instead of having the oxygen in the environment, and brought the substrate. When the surface of liquid metal, for instance, in this example, tin, is exposed to H2S, and we harvested it. The layer obtained from this is supercrystalline. Very interestingly, it doesn't have any subdomains either. It's a single domain crystal. As you see, for instance, in this transmission electron microscope imaging, that all crystals are all in the same direction and highly crystalline. It's one layer, and we did the piezoelectric measurement and electronic property measurement. The band gap was 1.4 electron volts. Is one of the only materials that when you go to smaller thickness doesn't open the band gap. It's very fascinating, actually. It's a fantastic band gap because it's very similar to that of silicon. So that means you can basically harvest energy of light, of sun from this as well, but we didn't do it. Here we just use the piezoelectricity. The carrier mobility is very high, 35 cm square per volt second. Carrier density is very high. As a result, we could see large current if we, when we made a very simple piezoelectric flexible device, as it's 2 dimensions flexible. And as you see, we put it on our finger, we just bend our finger, it produces 150 millivolts of current, voltage, and relatively large currents. Yeah, basically the highest power that anyone obtained around a 2-dimensional material piezoelectric. How about other things? Look, there's the surface of liquid metal is atomically smooth. It's the mirror. It's a real mirror. And it's very active because you have free electrons on the surface. You have this highly super reactive electrical double layer on the surface that can catalyze everything. Can we use the surface to form 2-dimensional material and reduce things or oxidize things on this very active reaction, radioactive media? Surface super smooth media. For instance, we use potassium permanganate on the surface. Manganate ions come to the surface, they transform into manganese dioxide, which is 2-dimensional. And they naturally exfoliate themselves. Basically, if you have a permanganate potassium solution and the DR water, and put a droplet of liquid, the color goes down from very strong purple into transparent after 1 or 2 days. And you get very, very interesting 2-dimensional, fluffy, exfoliated material layers on the surface of liquid metal. Seeing this kind of reactions happening, we thought, okay, how about we try, see whether we can make 2-dimensional carbonaceous material on the surface, because no one has ever made this at room temperature at the time. He said, okay, if it's this reactive, we should be able to do the reaction at room temperature. So we did a DFT calculation. We see that we can split the CH bonds if we use a precursor that has a CH bond. So we tried methanol, ethanol, isopropanol, and glycerol, for instance, and acetone, simple molecules that has this kind of materials. And then we use precursor that has nitrogen in them, like acetonitrile and pyridine, and more complex rings as well. DFT also shows that, yeah, when the splitting happens, radicals are formed, and eventually these radicals are penetrated into liquid metal, and they come out and produce CC bonds. So that was very interesting. So it seems that we can make 2-dimensional material. These CC bonds, after become very large molecules, they cannot remain dissolved. They come to the surface. Here are the examples. If you don't have a precursor on the surface, we apply a voltage against a reference electrode, the liquid metal deforms, and no 2-dimensional material, no color changes as seen on the surface. Now, if you do this with precursor, you see a 2-dimensional material is formed, exfoliate itself, and basically you can take your tweezers and take it out. Okay. So we did it in an electrochemical setup with the different precursors that we showed to you, and as you see, some of the precursors broke down, and Raman showed that the D band and G band of these 2-dimensional materials are very broad. So these are not really graphene material. They're not highly crystalline. When we did the TEM imaging, as you see, they are 2-dimensional, but are broken 2-dimensional. They're made of many domains, which are very close to each other. It's highly porous, which are fantastic for making battery electrodes. But we wanted to see whether we can make graphene or graphene oxide out of this as well. So what we did, instead of letting that liquid metal deform, we just painted it on the surface of an electrode, like copper electrode, so it doesn't deform anymore. We apply the voltage, and also voltage helps to self-exfoliate, because electrophoresis then, after it becomes a little bit thick, takes it from one side and land it onto the other side electrode. The fantastic thing is if you use a specific precursor, for instance, if it's nitrogen is included in this precursor, you get nitrogen doped. If fluorine is in this precursor, it's fluorine doped. You can dope it at the same time, this graphene oxide material, when you are forming it. Now, another thing that I want to talk to you is about crystallization. Very, very fascinating image that you see here is a cesium, cerium inside liquid metal gallium. Or it's interesting because if you look at the phase diagram of cerium versus, for instance, gallium, it doesn't dissolve more than 0.1% into gallium. But here is 3% of cerium. So what happened that when you increase the second element that you add to your liquid metal at higher concentration than solubility limit, it produces nucleation, and it produces nanoparticles of secondary element. These nanoparticles, many of them come to the surface, remain close to the surface. So I was very fascinated by this material that we obtained. And also we can see the TEM images. The crystalline is there, liquid metal, which is amorphous, is there. I said, all right, what if we use this as an electrode for transformation? Basically, transformation of CO2, which is our greenhouse gas, into something else. We did this. So we put this cerium, we add 3% of cerium into gallium. It produces really hot, not super fully stoichiometric cerium oxide, so C2O3 on the surface. And we put everything in a secondary liquid with bubbled CO2 gas. So CO2 gas comes around this, and we apply the voltage. This CO2 gas breaks down on the surface and produces stoichiometric CeO2, fully oxidized cerium oxide. But this applied voltage reduce the surface back to C2O3, so it continues. But the fascinating thing is CO2 breaks down, produces these CC bonds on the surface, it produces the flakes of C on the surface. And the onset voltage to produce is very, very low. It's only 310 millivolts. So the total energy needed is very, very low. And the conversion efficiency for Radeke efficiency is very high. At minus 1.8 volts is almost 80%. And it keeps continuing happening. Everybody is avoiding converting CO2 into anything but liquid or gas because they remain on the surface and coat the surface. So here caulking is not happening because the CO2 doesn't stick to the surface and self-exfoliate. So we can, for the first time, have a system that transforms CO2 into basically carbonaceous material that we can take and burn again. Phase separation this is the last part of this topic. Basically, the classical phase separation is like you put two metals together and then at high temperature you melt them. They mix, entropy is high, so elementally they are mixed, but when you cool them down, they separate themselves into crystals, phase-separated crystals. Here, bismuth and tin. Bismuth melting point is 271, tin is 232. But they have a eutectic alloy with a much lower melting point temperature of 139 when bismuth concentration is 57% of the total volume, of total weight. So basically, we sonicated everything at relatively high temperature of 250, 70 degrees. We made these nanoparticles of metals, bismuth and tin in different ratios. We use them as they are, or we anneal them as a photocatalyst. Before annealing and use them as metal, if you break one of these particles and open them and look at them, microparticle, before you sonicate them for too long, you see very interesting classical metallurgy formation of crystals. So basically, when we're talking about 20% bismuth, 80% tin, we have these nano rods of bismuth in a pool of crystalline tin. If we have 80% bismuth and 20% tin, Then we have crisscrossed two-dimensional metals of bismuth and tin. These are fantastic metals. Actually, they are topological insulating materials. Somebody has to extract them and use them. Or if we use 57% bismuth and 43% tin, which is eutectic alloy, the highest entropy of these two mixes. When you cool them down, because the entropy is very high, they don't form the crystals. They form fibrous materials like those. Now, as you see, there are gaps. These fibrous materials are full of loss of characterization and do the sonication at the same time. You see, rather than having only tin oxide, as I mentioned to you, there is a competition between bismuth oxide and tin oxide. Only tin oxide in the bulk is formed on the surface, but because we do sonication, we have bismuth oxide, tin dioxide, and tin oxide from the surface. So the surface is really has a variety of materials. The core has more grains. We have more grain boundaries for this eutectic alloy, and we have lots of higher density line surface defects and edge dislocation. All these things says that we have a very good catalytic metallic material which is covered with metal oxide. We use it for CO2 reduction reaction. This is not in liquid form, this is in solid form. So this is classical electrochemical reduction into formation, into formate, which is a liquid. The voltage which is applied is very low, Faraday efficiency is very high, 78%, and the enhanced grain boundaries here using the liquid metal process for the formation of these for nanoparticles help us. So it's all not about liquid, it's about the process that also can improve and give you opportunity to make the material better for catalysis. Or we can anneal it and add different materials, and by mixing and composing different things like cooking, adding different ingredients, you can make the material less or more selective into catalyzing something against catalyzing any other compound. Here, for instance, we're talking about Congo red and methylene blue. By adding silver, by adding less or more indium and tin, we could make the material, it's a photocatalyst, more or less selective to catalyzing one dye against the other dye. So basically, the talk is finished now. I just wanted to give you some of the examples of this world of liquid metals and the reducing dimensions in liquid metals, how you could use the chemistry, how you could use the physics, and how to open our eyes to see the properties that liquid metal as a solvent, like any other solvent, give us to produce materials that otherwise we don't have access to. I hope that it gives you some vision to continue this and have your own discoveries. Of course, I would like to thank you all to be here and listening to my talks. And I would like to thank, of course, all those past and present members of my group who were involved, and collaborators, and also the fund providers. Thank you very much.
Kourosh, thanks a lot for your really very nice talk. So there's quite a lot of people who have joined in the meantime once you started. So I think for all of those who missed a little bit the first part of the presentation, we'll be posting the recording of this lecture on the IEEE channel in New South Wales.
Yeah, sure.
So I would like to ask the audience if they have any questions. I mean, the easiest is just to pop it into the chat box, but you can also just unmute yourself and ask questions. So we have already one coming from Murti. Murti says, are you getting any interest from semiconductor industry?
Yes, we had a few. Again, I cannot tell the names because it's recorded and it goes online. Yeah, we have a few actually. And
a follow-up question on that one, actually, I was going to ask you. So this is fascinating because it's actually electronics is certainly one domain, but there's so many other areas that it's a whole new toolbox that can potentially solve a lot of different problems. In terms of industrial potential also impact into industry, I was wondering, do you think there is a way to scale this up, potentially in an automated way that can really be done at large scale?
Yeah, actually, that's a very good question. Already we have a an automatic system in our lab now. Before we were doing everything by hand. We used to do this by hand. We realized, of course, hand shakes anytime we bring up and down this liquid metal to exfoliate the two-dimensional material from the surface. We could not get, the most ideal two-dimensional material we wanted to. We purchased a very accurate piezo stage that goes up and down by 1 nanometers. It became highly controlled. Now we can obtain very, very large scale. I'm talking about very large scale, centimeter by centimeter scale, rather than half a centimeter by half a centimeter scale.
Well, centimeter range is good.
Yeah, it's very, very large to our opinion. As you see, even with hand, we could get like 1 centimeter, 2 centimeter kind of dimensions. Now, with this one, we get like 10 centimeter dimension each way. And it doesn't have metallic inclusions anymore in them because it doesn't wrinkle. It seems that it's very viable to do this larger scale production upscaling. And there are tools available to do this.
That sounds fantastic. We have some other questions. So we have Dush asking, is the ITO glass printing facility, are ITO glass printing facilities available at UNSW, and what are size limitations?
Yeah, as I mentioned, something around 5 by 5 centimeters, we can do it, right?
So he's specifically interested in printed antennas on glass. Do you think it's possible?
Yeah, and glass is possible. Glass is SiO2. So it's polarized surface, relatively polarized surface. Of course, something like quartz is better. It's more polarized. So the van der Waals force is better. But glass is okay too, and it sticks to glass surface. It sticks to polymers, and you can harvest the two-dimensional material out.
So probably Dush will contact you in the next few or in the next few days. So then there is a question from Yang Yang. So he asked whether the printing facility is similar to, is like a 3D printing system, or how does it work?
No, it's just a stage that goes up and down.
All right.
Very, very similar to the stages which are used for AFM, atomic force microscopy.
That you don't need the 3D,
Yeah, no. So it has Z and Y and X. So if the Z is really high resolution, it goes up and down in nanometer range. Great.
So Albert Chin from Taiwan, he asks for, can we control the ITO with different monolayers, and what's the thickest one you can make, you think?
Yeah, so in the example that we published in that Nature Electronics paper, we showed up to 2 layers only, right? Because we used to do this by hand. Now, there are 2 ways of increasing the thickness. One is just put 1 layer after another. Now that we have the piezoelectric equipment system, we can do this up to 4 or 5 layers without adding many metallic inclusion and make really good quality materials. Or the other way is you can increase the thickness, but it becomes like a bulkier kind of material by increasing the ambient oxygen. So there are 2 different ways. Yeah, so
I noticed, so during your presentation, indeed, you mentioned that the ambient is quite critical for some of those layers.
So, exactly. So there is a critical number that you make it self-limiting or non-self-limiting. So just for each material that you want to deposit, you find where that number is, and you increase or decrease the, for instance, hydrogen sulfide that you want to go for sulfide compounds, or oxygen that you want to go for oxygen compound, above or beyond that limit, and you control the thickness.
That's very fascinating, and I guess it's just only the start of a lot more research
Investigation,
to be done. And of course, from IEEE perspective, anything that can be scaled up and potentially done together with industry would be fantastic. It
yeah.
would be really very nice to see. Yang has another question. He says, I assume the liquid metals can be formed with periodical arrangement with phase turning performance. I'm not sure what he means by that.
Yeah,
So,
it's possible. That means we go from one layer to another layer, I think. If it's the case,
oh, yeah,
the only problem is these layers are not registered on the top of each other. That means the alignment of the crystals are different.
Right. And so you said already something about it, but you can really make heterostructures by just supplying different.
But this is not the deposition. It's a placement of one layer onto another. For instance, when you do MBE, you get the second layer, which is in registry with the first layer in terms of crystal. But these are not in registry, the layers with each other.
Right. I see. So
because the mechanical placement.
Yeah, I see. This is actually an area which is really interesting. I had started looking into that when I was still at IMEC because we wanted to get away raw nanowires with something that wasn't gold. And we stumbled upon a lot of low melting point metals that were really helpful to grow nanowires. So 1D structure in that case. But yeah, it was more of a bulk.
So actually we can make one-dimensional materials as well, but they haven't published it, so I haven't presented it. It should be published soon.
All right. So let's see if there is any more questions from the audience. So everyone has appreciated your talk, Kourosh.
Thank you.
And so what's your next step right now in this area?
Just continuing. At the moment is to explore the most important thing is like dear water, like organic solvent. It's a solvent, right? So anything that we can do with any other solvent we can do here. That's an amazing thing that has been widely ignored by scientists to have these observations, because it's not transparent like water. It's not transparent like other solvent. When we don't see something inside, we ignore it. So you can use this solvent for creating nanomaterials inside. You can use this solvent for electrochemical reactions and many other things.
So I guess you're setting up a very specific facility at UNSW to...
No, it's cheap. You can do it at home.
In the garage.
Yeah. It's not as specific. Of course, characterization is very specific, you're right.
And scaling up, I guess, and control of the...
But synthesis is not as specific. You just have to see what you obtain and have a plan, have some observation,
So let me see if there's any more questions from the audience. Doesn't seem like that.
All right.
So Kourosh, once again, thank you very much for volunteering to give this lecture for us.
Thank you.
And thanks for on behalf of the audience as well. And as I said, we will be posting this lecture very soon. So I will send around the link to that for anyone who wants to re-listen to it.
Thank you very much.
So thanks everybody. And yes, so we'll be continuing posting our chapter activities. And so watch this space going forward. Thanks again, Kourosh.
Thank you. Bye-bye.
Bye-bye.